Hi guys, my name is Michael, and for today's lesson, I'm going to be focusing on the practice problems for Chemistry 10, Lecture 4. Okay, so we're going to first start off with the classification of matter. Matter is anything that has mass and occupies space. Matter is all around us, every day, everywhere. Matter can be classified as a pure substance or mixture. Pure substances can further be grouped as an element or compound, while mixtures can further be grouped as homogeneous or heterogeneous. What are some substances in your life that you can categorize in these terms? Give 2 examples each. The examples that I use for element are Fe, which represents iron, and C for carbon. For compound, I use salt, which is NaCl, and NH3 for ammonia. For a homogeneous mixture, I chose coffee and orange juice because typically with those mixtures, you can't really distinguish what things are placed into it. Whereas for heterogeneous mixtures, for sand and water, and orange juice and with pulp, you're able to see where the pulp is at. The same with the sand, you're able to distinguish that when it's in the water where it's placed. For number 2, chemical versus physical properties and change. Matter can undergo change. In your own words, without looking at the notes, define physical change and also chemical change. I put that for physical change. It's only changing the appearance of a substance, not its chemical composition. And for chemical change, it causes a new substance to change into a new substance with a new chemical formula. Okay, so we're going to categorize each change under the correct description of that change. Water evaporation, rusting of metal, burning of wood, bleaching your hair, rotting food, dissolving sugar, and melting butter. And one example of each change. So for physical change, I put that water evaporation, sugar dissolving, and butter melting. It's not necessarily changing its chemical property, but just changing its physical appearance. For chemical changes, metal rusting, wood burning, hair bleaching, and food rotting. That is more on the chemical side, not so much physical. Because of those chemical changes, new substances are being created. So for number 3, we're focusing on temperature conversions, looking up the conversion equation in your notes and solving the following temperature conversions. I added a temperature conversion formulas chart just to kind of use as the template for these problems from A through F. For A, it asks us to change 21 degrees Celsius to Fahrenheit. Using the table, we plug in 21 degrees Celsius to Fahrenheit, which puts us at 21 degrees Celsius times 9/5 plus 32, which gives us the answer of 69.8, which we round off to 70 degrees Fahrenheit. For question B, it asks us to convert from Fahrenheit to Celsius. We're given 112 degrees Fahrenheit. We're asked to change that to degrees Celsius. Using the chart provided, we're able to plug in the Fahrenheit for the Celsius degree equation. So we have 112 degrees Fahrenheit, subtract 32, multiply it by 5/9. When you do that, you get 44.4, which you round off to just 44 degrees Celsius. And as we're going through these videos, please feel free to pause it if you feel that I'm going a little too fast. For part C, we're changing from degrees Celsius to Kelvin. We are doing 25 degrees Celsius to Kelvin using the conversion chart. You can see that you plug in Celsius to Kelvin equation, which puts us to Kelvin equals 25 degrees Celsius plus 273.15. that gives us 298.15, which we just leave it at 298 kelvins. For part D, they ask you to change from Kelvin to degrees Celsius because there's not just one given equation for that. We have to put two equations in. First, we're going to convert the kelvins to Celsius, and then we're just going to reverse it a little bit. We're going to alter the equation that we have for Kelvin. So Kelvin equals to degrees Celsius plus 273. We subtract the 273, which gives us a new equation of degrees Celsius is equal to Kelvin minus 273.15. We substitute the 298 Kelvin, which gives us degrees Celsius is equal to 298K minus 273.15, which equals to 24.85, rounds off to 25 degrees Celsius. So for this one, we're just rearranging the equation given to solve for this problem. For part E, I'm converting from degrees Fahrenheit to Kelvin. We have 232 degrees Fahrenheit. So for this one, it's going to be a two-part conversion formula. So we're going to first start off with degrees Celsius. So we're going to plug in that 232 degrees Fahrenheit minus 32 times 5/9, which gives us roughly 111.11 degrees Celsius. We're going to plug that into the Kelvin equation. With that, it gives Kelvin is equal to the number we got from the previous equation. So it's 111.11 degrees Celsius plus 273.15, which gives us 384.26, which gives us 384 kelvins. For part F, it's asking us to go from Kelvin to degrees Fahrenheit. This is also a two-part equation. So we're going to first solve for Celsius and then afterwards solve for Fahrenheit. So we're going to use the Celsius conversion formula. So 505K minus 273.15 gives us 231.85 degrees Celsius. We plug that into our Fahrenheit conversion, which is 231.85 degrees Celsius times 9/5 plus 32, which gives us 450 degrees Fahrenheit. For number 4, potential and kinetic energy. Energy is defined as the ability to do work. That ability to do work can be saved or used. When it is being saved, it is called potential energy, and while it is being used, it is called kinetic energy. We have to indicate whether each of the following statements describes potential or kinetic energy. For the calories in a banana, that is seen as potential energy. For an apple hanging from the tree branch is potential, and the gasoline in your car tank is potential as well. The reason why I chose that is because it's being saved, not being used necessarily. For D, a jog is kinetic. For E, rolling down a hill is kinetic, and for your brain, thinking is kinetic, because that is using the energy to do those things. Okay. For number 5, the SI unit of energy is joule. A joule is very small, so kilojoules is more convenient to use. How many joules there are in 5525 joules? For that, we use the equation 1 kilojoule is equal to 1,000 joules. When you plug those in, you cross cancel the joules, which leaves us with kilojoules, and from that we get 5.525 kilojoules. For number 6, another unit for energy that is often used by scientists and nutritionists is a calorie. And for this, we're going to convert 3.5 kilojoules into cals, with knowing that 1 cal is equal to 4.184 joules. So we set up our equation like this. 3.5 kilojoules times what we know already is 1,000 joules is equal to 1 kilojoule. With setting it up that way, we're able to cross cancel the kilojoules, and from there we have joules, which is multiplied by 1 cal over 1.84 joules. The joules cancel out as well, which leaves us with 836.5, which we round off to 840 calories. For number 7, energy is in your food. When you come to Professor Nguyen's office hours to seek help, you are often offered a snack like Snickers bar. A fun-sized Snickers bar with a total mass of 17 grams has a total of 4 grams of fat, 10.5 grams of carbs, and 1.5 grams of protein. And if you look to your lower right, you'll see a chart that we can use as a reference for answering these problems. A review, what is the percentage by mass of the fat in this snack? From what we know already, we plug in at the very bottom for our equation the 17 grams of Snickers, and also what we know for the 4.0 grams of fat, and we multiply that by 100%, and that gives us 23.5% fat. Okay, using this table, we're going to calculate an estimate as to how many calories in one fun-sized Snickers bar. So, knowing that 1 cal is equal to 1 kcal, we're able to plug in these numbers to our fun-sized Snickers. So 4 grams of fat times the 9 cals over grams of fat is equal to 36 cals. 10.5 grams of carbs from our fun-sized Snickers times 4 cals over grams of carbs gives us 42 cals, and 1.5 grams of protein times 4 cals in a protein gives us 6 cals. The total is 84 cals. We round off, it gives us 80 cals. And that's it.